Hello, my name is Osam Ali, and I'll be talking about asserting expectations. Observation versus assertion. Observation is simply the act of the programmer watching the states and events of a system. Assertion is an automated observation technique that can specify a condition at particular points in a program. Observation is limited to small probes in space and time, but assertion can automatically cover a large area as shown in the example below. Basic assertions. Basic assertion is a straightforward process where the programmer puts a statement in their code that predicts a Boolean valued function or true-false expression, as you can see below. Assertion and macros. The macro implements an assertion, which can be used to verify assumptions made by the program and print a diagnostic message if this assumption is false. This example uses file and line macros to report the location of the assertion in the source file. Asserting invariance. Invariant is a condition that can be relied upon to be true during execution of a program or during some portion of it. It is a logical assertion that is held to always be true during a certain phase of execution. Precondition test guarantees that a subprogram will not be entered unless assertion is satisfied. Postconditions test guarantee that a certain set of circumstances will be true before exiting a subprogram. Ensure sanity. To ensure sanity, all one needs to do is to wrap each public method that changes the state into two assertions, both checking the sanity. This ensures that any infection that takes place in these methods is properly caught. And if all assertions pass, we can rule out time as an infection site. Locating infections. Precondition failure. This will check if a condition is true or false before running the segment of code. Postcondition failure. This will check if a condition is true or false after the segment of code was already ran. If all assertions pass, this means that the state is just as expected. Complex invariance. For complex data structures, specifying a pre- or post-condition may require the use of a helper function that checks for the individual properties. For instance, if a sequence is to be sorted, we need a helper function that checks whether the post-condition is satisfied. Helper functions used in post-conditions usually make useful public methods as shown in the examples below. Invariant and debuggers. Once one has a function that checks data invariance, one can also invoke it in an interactive debugger to check data sanity on the fly. A conditional breakpoint in GDP, such as shown below. Design by contract concept. The Eiffel language incorporates the concept of design by contract, where a contract is a set of preconditions that must be met by the caller, which is the client, and a set of postconditions that are guaranteed by the callee, which is the supplier. In the Eiffel language, a contract regarding set hour would be specified as shown below. Eiffel provides an invariant keyword, the condition of which is checked before and after every invocation of a public method. Defining invariance with Z. Formal systems. The most complete and unambiguous language we have is mathematics. And discrete mathematics is the basis for the several specification languages, such as Z. As shown below, the Z specification for the data class and its setHour method. It is easy to recognize the invariance as well as the intermixed pre- and post-conditions. Such a specification is obviously far more precise than a natural language version. JML, Java Modeling Language. The success of specification languages largely depends on their expressive power as well as the quantity and quality of available tools. A language that excels in both areas is JML, the Java Modeling Language. JML assertions are written as special comments in the Java code, recognized by JML tools alone and ignored by the ordinary Java compilers. Using requires and ensures keywords, one can specify the pre- and post-conditions of an individual Java method in the Eiffel style. Relative debugging. In some cases, the correct behavior of a program P1 is not specified explicitly by reference to another program, P0, the behavior of which is defined as correct. This means that P1 is supposed to behave like P0 in some central aspect or even in every aspect. During debugging, we frequently need to tell whether some program state is infected or not. Having a reference program P0 as an oracle, we can compare its state against the debugged program P1, and again, any differences is a potential infection or anomaly. Typically, such a comparison is done by having two interactive debuggers run in parallel, with the programmers comparing the individual results. Relative assertions. Comparing two programs and checking to see if they both have the same results. If they are both the same exact program, then they should both have similar results, if not identical, if the same exact set of tests were ran on them. Using a reference program P0, one can simply compare against the result of the reference program. This is a common scenario for regression testing. We feed P0 and P1 with the same exact input. Any unexpected difference in output is a potential error, or at least an anomaly, to keep in mind for further investigation. Memory allocation check. Using the GNU-C runtime library, which is default on Linux systems, one can avoid common errors related to heap use simply by setting an environment variable called malloc check. For instance, one can detect multiple delocations of heap memory. The core files generated at program abort can be read in by the debugger such that one is directly led to the location where free was called the second time. Electric fence. The electric fence library effectively prohibits buffer overflow. Its basic idea is to allocate arrays in memory such that each array is preceded and followed by a non-existing memory area. The actual electric fence, if the program attempts to access this area, the operating system aborts the program. Valgrind. Valgrind provides the functionality of electric fence, plus a little more. Valgrind detects read access to non-initialized memory, write or read access to non-allocated memory, write or read access across array boundaries, write or read access in specific stack areas, and helps with detection of memory leaks. Language extensions. Cyclones. Cyclone's central extension to C is the concept of special pointers, that is, C pointers with special properties. For instance, in Cyclone, one can declare a pointer that can never be null by using @ sign instead of the asterisk. The getC function retrieving a character from a file is such as shown below. Another interesting Cyclone feature is fat pointers. Fat pointers that not only record a location but bound information, such as the size of the area being pointed to. Such a pointer is declared by using question mark instead of asterisk. Using fat pointers, a function such as string length, determining the length of a string, can be declared as shown below. Assertions and production code. What do we do with the other assertions in production code though? The following are arguments to consider. The more active assertions there are, the greater the chances of catching infections. The sooner a program fails, the easier it is to track the defect. Assertions impact performance. By default, failing assertions are not user-friendly. Some of the tools it can be used is GML, which we talked about earlier, the Java modeling language. It is a behavioral interface specification language that can be used to specify the behavior of Java modules. It combines a design by contract approach of IFO and the model-based specification approach of the large family of interface specification languages, with some elements of the refinement calculus. Guard. Guard debugger is just a relative debugger used to compare programs in parallel. The key idea of relative debugging is to execute P0 and P1 in parallel and flag in any between the program states. The guard relative debugger, the assertion window highlights differences between the states of two program runs. Valgrind. Valgrind is another tool. Valgrind is an instrumentation framework for building dynamic analysis tools. There are Valgrind tools that can automatically detect many memory management and threading bugs and profile your program in detail. You can also use Valgrind to build new tools. Purify, a more efficient way. When I say efficient, I mean smaller code size, less execution time, and less memory usage. Is not to interpret the machine code, but to instrument it. That is, to include extra code at memory accesses to update and check shadow memory. This approach is realized in the Purify tool, which detects the same class of errors as Valgrind, but in a more effective way. Programs instrumented with Purify have a typical slowdown factor of only 5 to 10. Purify also comes with a nice GUI as well as phone support from IBM. Purify has a long record of successfully checking arbitrary programs. Experienced programmers routinely validate the heap integrity with Valgrind and Purify or similar tools, just for easy elimination of a failure source and an extra ounce of confidence. Ensure++. Ensure++ is a commercial tool that detects memory problems by instrumenting C and C++ source code. It is therefore available on a number of platforms. Why use Ensure++? It helps with memory error detection, unparalleled depth and precision, runtime error detection, compile time error detection in threads, and dynamic memory visualization. Cyclone. Cyclone is a safer dialect of C programming languages. Cyclone's central extension to C is the concept of special pointers, that is, C pointers with special properties. To prevent memory errors in a low-level language, consider using a safer dialect such as Cyclone for the C language. These are some of my sources that I used, and I hope you have a great day.